In multi-tenant MCP systems, security starts with clear boundaries. Every request must carry tenant, user, workspace, and environment context end-to-end, so data, credentials, tools, caches, queues, and APIs never bleed across customers. So far, we've built the foundation, how MCP servers are structured, operated, and hardened. We then added secure access control through authentication, authorization, scopes, delegation, and consent. Now we address the production question that comes next. Once someone is allowed in, which tenant's data, tools, and systems can they access? The risk is straightforward. MCP servers do more than answer questions. They can run tools, touch databases, use credentials, and write logs. If tenant boundaries are missing anywhere in that path, one customer's context can leak into another's. Isolation has to be enforced by the server every time. Before enforcing isolation, define what owns what. A tenant might be a customer, an organization, or a business unit. Within it, workspaces and projects create smaller boundaries for collaboration, data, tools, and operations. Users, teams, and service accounts act inside those boundaries. The key design rule is to make ownership explicit. Every permission check should carry identifiers such as tenant ID, workspace ID, resource ID, and user ID. Do not infer access from names, email domains, or UI context. A clear hierarchy makes authorization predictable, auditable, and much harder to bypass. Once ownership is defined, tenant context must travel through the entire request path. Extract it from trusted identity data, such as tokens, sessions, or identity provider claims. Then normalize those values into a server-side context that includes tenant, organization, workspace, user, and environment. Authorization uses that context for policy decisions. MCP processing must pass it explicitly into tool handlers and service clients, rather than relying on globals or user input. Finally, every query, API call, trace, and audit event should include the same context, so access is enforceable and investigations are reliable. The safest rule is simple. The application decides the tenant, not the user, and not the model. Use sources that are already authenticated, such as signed identity tokens, server-side sessions, identity provider groups, or verified gateway headers. Everything else is input. Prompt text, query strings, tool arguments, and model-generated JSON can be manipulated, so they should never become tenant authority by themselves. A strong design centralizes tenant resolution in one service or middleware layer, so every request follows the same validation path before data access happens. Enforcement must happen inside every tool handler, not just at the edge. Start with a server-generated request context that carries the tenant, user, roles, and workspace. Build database access so the tenant filter is automatic. For example, every query includes tenant ID equals CTX tenant ID by construction. Then validate incoming identifiers against that same context, because a valid project ID may still belong to another tenant. Before any mutation or external action, check both permission and ownership. Unsafe handlers usually fail by forgetting just one of these steps. Authorization should evaluate the full context, not just a role. The policy question is, can this principal perform this action on this resource within this tenant and workspace under this environment? Tenant membership is only one input. A workspace viewer may read, but not delete. An org admin may reach more resources, but still only within defined tenant boundaries. If tenant or workspace context is missing, the safe answer is deny. Every decision should also be logged with enough detail to explain why access was allowed or blocked. The boundary cannot stop at the MCP server. Every downstream hop must preserve it. For sensitive systems, use tenant-scoped credentials, such as per-tenant tokens or service accounts. If a shared credential is unavoidable, the application must add tenant filters, policy checks, and auditable context before each call. Pass tenant identity through headers, metadata, or client parameters, so databases, APIs, queues, and vector stores can enforce it. Be careful with batching. Mixed tenant batches are safe only when every item carries verified tenant context and is checked independently. Storage isolation is a spectrum. Row-level isolation is the cheapest and easiest to scale, but every query, policy, and report must enforce tenant filters correctly. Schema-level isolation gives each tenant clearer structure while still sharing database infrastructure. Database-level isolation creates a stronger failure and access boundary, but increases migrations, monitoring, backups, and connection management. Account or project-level isolation is the strongest option, useful for regulated or enterprise tenants, but it carries the highest cost and operational burden. The right choice depends on risk, scale, and customer expectations. Secondary stores are part of the tenant boundary, not plumbing outside it. Caches need keys that include environment, tenant, workspace, resource, and a content hash, so one tenant never receives another tenant's result. Search indexes and vector stores need either physical tenant partitioning or mandatory metadata filters on every query. Derived data matters too. Embeddings, summaries, and tool outputs must carry ownership tags. The dangerous pattern is a global cache or unfiltered semantic search that feels fast, but silently crosses boundaries. Reuse outputs only when the design proves it is safe. Cross-tenant leaks usually do not start with broken login. They start with ordinary engineering shortcuts. Imagine a support search tool that returns another customer's tickets. The user was authenticated correctly, but the query missed a tenant filter. The search ran against a shared index. Then the result was stored in a cache key that included the search term, but not the tenant. Now the wrong data can be replayed quickly and invisibly. The same pattern appears with reused service tokens, shared queues, and default queries. That is why isolation has to be enforced at every layer. Environment segmentation is a practical safety boundary, not just an organizational label. Development should use synthetic data and disposable credentials, so experimentation cannot touch customers. Staging should mirror production behavior, but with anonymized data and restricted tools. Production gets the strongest controls because it holds live data and sensitive actions, such as billing or destructive operations. Give each environment its own MCP deployment, URL, secrets, database, and policies. Then require explicit environment identifiers and checks to stop accidental cross-environment access before it happens. Isolation also has to be verified continuously. Treat every release as a chance to prove the boundary still holds. Automated tests should try cross-tenant access and missing tenant context. Code checks or query wrappers should catch unsafe, unscoped queries before deployment. In production, audit logs need enough context to explain every decision: tenant, workspace, user, tool, resource, and outcome. Monitor for signals that suggest drift or attack, such as denied request spikes, tenant mismatch errors, unusual data volume, and policy failures. Tenant isolation is not a single control. It is the production model that ties identity, authorization, data design, downstream access, and operations together. Trust tenant context, propagate it, enforce it everywhere, and log it. Pay close attention to hidden risk in caches, queues, indexes, APIs, and defaults. Strong environment boundaries complete the model. Next, we move into secrets, tokens, and auditability.